The cerebellar system contains a huge number of neurons, and it's clearly taking up a significant proportion of brain resources, but it appears to run in parallel with other brain systems. So the question is, what's its role, and why is that role so important that large physiological resources are devoted to it? One clue is the role that the cerebellum plays in what's called eye blink conditioning. This can give a certain amount of insight into the role of the cerebellum in general. So what's eye blink conditioning? When an eye experiences a puff of air, there's an automatic blink response to protect the eye. You don't need to think about it, it just happens. But there's generally a delay between the puff and the blink. The time it takes for the sensory input to indicating a puff to be processed through the brain to generate the outputs that drive the muscle movements that control the eyelid. So, displaying this in time, if the puff of air arrives here, the blink will occur here. Now, suppose that over a number of occasions, an audible tone is presented that starts before the puff and continues after the puff. If it always begins exactly the same length of time before the puff, this approach can train the brain to respond faster. After a number of trials, the eye blink starts to occur a fixed time after the start of the tone, coinciding with the peak of the puff. And this learning is called eye blink conditioning. Blocking the connections between Purkinje cells and cerebellar nuclear cells, at least in the brains of rabbits, disrupts the effect. So the cerebellum is playing a role in this kind of learning. If the tone and the puff of air don't overlap in time, conditioning still occurs, but now it depends both on the cerebellum and on the hippocampus. So the implication is that the cerebellum is concerned with timing, while the hippocampus is needed if more complex associations have to be created. Another line of evidence is the kind of deficits that occur when the cerebellum is damaged, for example, following a stroke. In a normal person, if you were asked to put one finger high in the air, then move it to touch your nose, you'd make a short, smooth movement. But with cerebellar damage, the movement can be much more irregular and inaccurate. When a normal subject is asked to rapidly alternate between two hand positions, such as put one palm on top of the other, then repeatedly flip the top hand over and back again as rapidly as possible. When a normal subject is given this task, they again execute smoothly. But a person with cerebellar damage, in those people the movement may be much less well controlled. And cerebellar damage can result in other motor symptoms like erratic walking similar to a person who's drunk. There can be deficits in skilled voluntary movements like playing a piano, or problems with speaking like slurred words or uncontrolled variations in the loudness of words within a spoken sentence. It's also interesting that although there are these deficits, sometimes a motor skill can be recovered after damage, perhaps with a different part of the cerebellum relearning the lost functions. But the role of the cerebellum isn't limited to motor movements. In some experiments, sandpaper was passed over the fingers of human subjects, and the cerebellar activity monitored by MRI. If the subjects were asked to passively experience the sensation, the activity in their cerebellar dentate nucleus was relatively low, compared with a situation in which they were asked to assess the roughness of the sandpaper. Dentate nucleus activity has also been observed when subjects attempt to perform a task that involved moving pegs on a board in accordance with some rules. The dentate nucleus activity became greater as the difficulty of the task increased. In general, there's quite a lot of evidence that the cerebellum plays a role not just in motor movements but in higher cognition. Higher cerebellar activity is seen during tasks requiring imagination, and cerebellar deterioration can result in deficits in planning capabilities. So, in summary, the cerebellar system is a large anatomical structure with huge numbers of neurons that appears to offer a parallel path for performing a wide range of behaviors, and it seems to be critical for managing timing in the performance of tasks. So, at this point, I've concluded the description of the major anatomical structures, and that also ends the description of the physical brain, its anatomy, physiology, and chemistry. The next step is to describe how some theoretical considerations constrain the architecture of any system that has to learn a complex combination of behaviors. And then we'll go back and see how the constraints can help us understand what different brain structures are doing in information terms and why they have the structures they have.